back, ladies and gentlemen, to another exciting AP chemistry video. I'm super stoked today to talk to you about solutions, mixtures, and solubility. Now again, you've probably had a lot of this material before, but we are going to apply it and take it to the next level, because not only do you need to know how to do calculations that are related to solutions and mixtures, you also need to be able to understand different methods of separation, dilution, as well as making individual solutions. Let's get started. Today, our student learning objectives are the following. You should be able to solve for and use molarity as a conversion factor between moles of a variety of substances. You should also be able to explain and draw models of solutions, describe methods of mixture separation, explain solubility of solutions, describe how to properly make a solution, and calculate using the dilution formula. Seems like a lot, but we'll get through it one step at a time. Now, solutions themselves are homogeneous or homogeneous mixtures, and that can be either solids, liquids, or gases. For example, brass is a mixture or a solution. Milk is a solution. Okay? Salt water, sugar water, Kool-Aid is a solution. It can even be a gas. The air that we breathe is a homogeneous mixture of nitrogen, oxygen, carbon dioxide, and other gases. So solutions can be any state of matter. The solute is what's defined as what's being dissolved. So if we're looking at Kool-Aid, we're dissolving the Kool-Aid powder. The solvent is what you're dissolving in this case water. And both combine to make the solution. Now, a solution that has undissolved solute is saturated. If it has less than that, it is unsaturated. So if we look at the examples here on the bottom, the saturation point of NaCl in water is 36 grams per 100 milliliters. I can take 30 grams of NaCl and completely dissolve it in the solution. There will be no particles left over. That solution is unsaturated, meaning that I can still dissolve more of the solute in it. If I take 40 grams of NaCl and dissolve it in 100 milliliters of water, the maximum I can dissolve is 36 grams, meaning that 4 grams of NaCl will remain undissolved no matter how much I stir it. Now, the only way I could get that to dissolve is to add more solvent. That would increase the amount of solute that is able to be dissolved. Okay? And when we look at on a molecular level what happens when we dissolve an ionic compound, you can see here that the sodium and chloride ions separate from one another in the ionic compound. The Na with the positive charge is attracted to the oxygens with the negative charges, and the chloride ion is attracted to the hydrogens with the positive charges, referring back to some of those intermolecular forces that we talked about previously in this unit. So how do we determine how concentrated a solution is? If you remember previously, we've used mole fraction as a way to look at gases, and in solutions we typically use molarity, and molarity is just simply moles of solute divided by liters of solution. Now do keep in mind that this can be used as a conversion factor between moles and liters. So if I'm given liters of something and I need to get moles or get moles to be able to do a stoichiometry problem, I can use molarity as a conversion factor. For example, 1.00 big M represents 1 mole per 1 liter of solution, and then I can use that as a conversion factor. Also keep in mind that the molarity of the ions is determined from the molarity of the solution and the formula. So 1 molar solution of CaCl2, if I were to dissolve that in solution, would contain 1 mole of Ca, but 2 moles of Cl because of the chemical formula. So do keep that in mind, especially when you're drawing out solutions, is that if you were to take something like CaCl2, let's say you were to draw a solution that had 5 Ca ions in it, you'd have to draw 10 Cl ions in it in order for it to be accurate if you were to draw it out in solution. Speaking of drawing it out in solution, this is exactly what I'm talking about, utilizing different colors and different shapes of ions to represent particulate matter in solution. So these models show those particles in solution. If something is insoluble, for example, AgCl, it's going to just be a large chunk of material at the bottom. You would not see it break apart into its individual ions. Think about the solubility rules that have been talked about in previous classes. If it is soluble, it will break apart into its individual ions. And be sure to represent the particles in the correct ratios. If it is insoluble, it will not break apart, and the compound will stay at the bottom. You'll see quite a few of these on some of the AP questions we'll take a look at a little bit later on. So how do we separate solutions? This can be a bit of a challenge. Well, there's really two key ways that we're going to look at in this class. The first one is through paper chromatography. You may have done something similar to this when we looked at chlorophyll in biology class. You can take chlorophyll, you break apart a leaf, and then you rub that on some filter paper. You dip it in some solvent, and that solvent actually travels up the filter paper using capillary action. Smaller ions are going to move up faster than the larger ones. As a result, it's going to actually separate the individual ions, which allows you to see what's in the solution. This is great for things that have different ions in it, because the different ions have different masses, and as a result, they're going to travel up the filter paper at different rates. So you'll be able to see different bands on the filter paper themselves. We'll actually do a lab over this a little bit later on. Another way that we can separate solutions is by using a process called distillation, which separates solutions based on the differences in boiling points of the components of a solution. So how this works is that you have your mixture in a round bottom flask, and it's heated up using a Bunsen burner or a hot plate. The mixture is heated up slowly until one of those components begins to boil. That gas then goes up the fractionalizing column, and then it gets to the top. As the gas goes to the top, it actually ends up going through the condenser. The condenser has cool water that's running through it, which changes that gas back into the liquid state, and it's collected in the Erlenmeyer flask that you see to the right. So two ways we separate solutions. We use chromatography paper, with paper chromatography, funny. Or we can use the process of distillation, which looks at differences in boiling points. So looking at solubility, liquids that mix in proportions are miscible, and if they don't dissolve, the term we use is immiscible. So miscible if they dissolve, immiscible if they don't. We use the term like dissolves like. Typically molecules that are polar tend to dissolve in those that are polar, and nonpolar with nonpolar. So do keep that in mind, that the polarity of the individual molecules that you're dissolving, as well as the solvent, are very important to determine if it actually dissolves. Now, solubility can be affected by a variety of factors. One that it's not affected by is pressure, unless you're like dissolving a liquid into a gas. Think about carbon dioxide and water. In order to get that to happen, you have to put it under pressure. Think about like a soda stream machine. There's a lot of pressure that's put under that. That allows the carbon dioxide to fuse or dissolve into the liquid. It's the same with cans of Coke. Temperature is one factor. Another one is surface area. Things that will dissolve faster if they have a higher surface area. Temperature is another one that's discussed here below, and temperature can actually affect how much solute is dissolved, not just the rate at which it dissolves, as well as agitation or stirring. That can affect the rate at which a solution dissolves as well. So another thing we're going to look at here is the dilution formula. Now, solutions are diluted to make new concentrations and volumes of new solutions. The key way to remember this is M1 times V1 equals M2 times V2. Knowing the various molarity and volumes can help determine how much water you need to add to dilute the solution. So be careful about the wording of some of those problems. Some of the wordings of those problems will ask you how much water you need to add to it. So you need to take into mind the volume which you had originally. Okay, we'll look at some of those problems a little bit later on. But like, for example, this problem down here below just asks how many milliliters of a solution are required to make 525 milliliters of this solution. So you would just need to be able to solve for V1, and you get how much of the 2.50 molarity NaOH solution you would need. In some instances, it's going to ask you for the second volume. Remember, that's the volume that you get after you dilute it. So you're going to need to subtract the original volume from that second volume in order to determine how much water you add. Speaking of making solutions, the best way to do this is using a volumetric flask. It has a high volume and has a narrow neck, and that narrow neck actually provides excellent accuracy, even more than that compared to a graduated cylinder. The way we make the dilutions is we add the solids first, then dilute the solution with water until the final volume is reached. Okay? So we'll practice with this in lab as well. Hey, hope you guys got a lot out of this video. We'll talk more about this in class and do some practice problems here in just a little bit. Take care, guys. Have a great day. We will talk to you later. Best of luck, and we will see you next time. Make sure you like and subscribe, JLand Bio, and shop merch. We'll talk to you later, guys. Bye-bye.